The first talk is going to be by Lucas from Google. He's going to talk about Triada, the past, the present, and the hopefully not existing future. So let's see how much fun Lucas has with Android. Lucas is over there being put the mic, and he will be on the stage right now. Let's give him an applause while he...
Okay. I'm Łukasz Siewierski, and I'm a reverse engineer at Google, as was mentioned. And I spend my day looking at apps and looking at apps for badness. And perhaps surprisingly, today I won't be talking to you about an app. I will be talking about something that's more pre-installed or part of the operating system. But we will start with an app, and this app will be a routing Trojan, fairly known routing Trojan. It was first discovered and described in early 2016. And back then it was a regular routing Trojan, so it rooted the device and then did some badness connected with the root privileges. And then we will move on to a system-level backdoor, which was the next evolution of this particular family. And then I will talk a little about how we reached out to the OEMs and tried to solve that problem. So let's start with some historical information and some information about Triada routing Trojan. It was first described by Kaspersky in March 2016. And it used old exploits to gain root access on the device. By old, I mean the newest exploit that I've seen worked only on Android KitKat, which is Android 4.4. And when it got that root access, it dropped an SU binary. SU binary is a binary that allows any other app to elevate itself to root. But this particular SU binary was a non-standard one, and the non-standard part of it was that it required a password in order to run. So the app that wanted to run this SU binary and get the root access had to know the correct password. And you can see the routine that checks for that password here. And the password is just a number of different letters and numbers starting with AC. So Triada had a very complex infection chain. There were many, many components. There were many different apps that got dropped. They had different kind of features, and they tried to do different things. So they all wanted to use that SU binary to do different things. And I kind of lumped all those things together. So some of the components of Triada tried to install apps on the system partition. For those of you who don't know, removing an app from the system partition is slightly more complicated than removing a normal app. It also tried to turn off Google Play Protect, which is our anti-malware solution. It tried to clean the device, and now by cleaning the device, they mean a kind of a space management system. So because Triada was mainly targeting low-end devices, they tend to have a lower disk space in general. So they tried to make sure that there is enough disk space to drop new components and remove all the ones that they didn't want. They also made some of the files immutable, and that is done through a change attribute command. And if you do something like that to the file, then you have to first remove the immutable flag from the file in order to remove it. So again, a kind of a persistence mechanism. And it also used OAuth tokens on the device. As far as I know, they never left the device. The only thing they used it for is to install some apps from Google Play, so it accessed the OAuth token and then installed other apps. And one other thing that it did, which I found quite interesting, is it tried to inject into other processes' memory. Again, you need root to do that, so obviously you need root to do all that features. So it was relying on having a successful exploit, and it injected into 4 different browser processes. And it injected using a framework called Droid Inject SO. And that framework has a specific, it takes a specific ELF file, a native code file, and then it ptraces into a remote process. When it ptraces into a remote process, it maps a memory address in a remote process and then has a very small shellcode, and the only purpose of that shellcode is to load the ELF file, in this case, inject data, so, and then run a specific function that is being exported. Okay, and there was another thing. And another interesting thing was that they used a very specific decryption scheme, and that decryption scheme is double XOR. Because, you know, double XOR is stronger than just one XOR. So you can see a loop here when they went through a loop twice with 2 different passwords. And I gave you, they used a number of different passwords, and they used different passwords for CNC communication, they used different passwords for strings, for assets. All of this was encrypted using a number of different passwords, and I chose my 2 favorite ones that were used in conjunction, and I bolded the second letter because it's the same in both passwords, which I guess you can figure out what that means for the double XOR encryption. So yeah, they used a very specific form of encryption which helped us with identifying more apps. The problem with that kind of approach is that if you are rooting the device, you are relying on exploits to do all the work. And the problem with newer Android versions is that it's very hard to exploit it, and it's very hard to exploit it reliably. So that, in addition to our own detection mechanisms that were based on some IOCs, resulted in a very sharp decline of triada routing Trojan on devices, because people changed their devices to newer versions and all that. So the authors decided to kind of choose a different path. Instead of fighting with detection and trying to get exploits, which are, again, more expensive, they decided to put a system-level backdoor, a backdoor that was part of the system image on some low-end Android devices. Again, they were targeting the low-end market. So this system-level backdoor was, in fact, just one line of code that jumped to a completely different subroutine and completely different part of the code. And this additional line of code was present in the log function. And when you think about it, it's a very creative way to, it's a very creative place to put a backdoor in, because every single app on your device probably will log something at some point, right? So every single app will execute the log function, and every single app will execute this particular line of code because it was, again, part of the system image. So if you have a backdoor in this place, what you are allowed to do is you are allowed to run in a context of any app that logs something, which is, of course, very good for the malicious actors. And this version was first described by Dr. Webb in July 2017. And the string that you can see here is a part of the configuration. So that bunch of letters and numbers actually translates into different configs and was different based on the different devices. And you can also see a familiar code structure. So let's start with the strings first. As you can see, the strings are kind of obfuscated. And I don't know if you know that, but generally in the Android operating system, we don't obfuscate strings, and we definitely don't use XOR to do that. So if you see a bunch of strings in an Android library, that probably means that there's a bunch of encrypted or obfuscated strings. That probably means that there's something wrong with it. And when I looked at the function that decrypts those strings, it looked like you can see on the right-hand side. So what you can see on the right-hand side? You can see 2 loops. And you can just imagine that every one of those loops had one XOR instruction in them, because it was in fact true. So again, double XOR in a completely different part of the code. This time it was, of course, not implemented in Java, because everything that they did on the system level was implemented in C, C++ in native code. And they also did code injection, basically like the old version. So the code injection was rewritten, and it wasn't as straightforward as in the standalone version. They introduced a new file format. I'm calling this MMD file format, but just based on the magic bytes that start every file. So those bytes are MMD. And after magic bytes, there is a hash of the file, and then there is a hash, of the decrypted file, and then there is the file length, and then there is the actual encrypted file. As you can imagine, all of those files were encrypted using, again, double XOR. Obviously, because that's the only encryption scheme that's being used throughout the whole triada. And all those files had something in common. So then their name was an MD5 hash of the process name, and then some other characters that were not that important. Actually, adding 36 to the mix kind of threw me off because it's numbers, so the length of the file name wasn't exactly the length of the MD5. But the MD5 hash was the MD5 hash of the process that they were targeting. So whatever code was in the encrypted portion was being injected into the process that had this particular MD5 hash, which again is a kind of anti-analysis measure because you have to figure out which process name maps to which MD5 hash. Fortunately, they were using very popular process names, so it wasn't that hard to figure that out. And the process name that they were using, we were able to find two different injections. One was to com.android.systemui, and that injection had a very simple reason. So back in Android Lollipop, we deprecated get running tasks permission, and you are not able to get all the running tasks on the device. And also, there was a new permission introduced that is get real. This is called get real tasks. And SystemUI, as it's a part of your system user interface, has that permission in order to list all the running processes and tasks. So what they did is they really wanted to list the top running process. And they wanted to list the top running process in order to display more context ads, I don't know, something like that. And they did so through a code injection, and then they communicated with the system UI. Any process that wanted to could communicate with the system UI and send a specific intent to that system UI. And if it sent that specific intent, system UI would simply run get running tasks and get the real running tasks and then respond using a different intent. So not only you had to know the intent that you had to send to system UI, but you also had to listen on the incoming intents to get the result. And this kind of communication was also part of their another code injection. And the other code injection was in the com.android.vending, which is Google Play Store. And for Google Play Store process, they had 5 different commands, and there are 10 here because they used a command enum, and that command enum had both the request and the result. So again, the communication was there was intent being sent to the Google Play Store app, and there was a response from the Google Play Store app. And if the intent that was sent to the Google Play Store app had 1, that means that it was a download request, and the response had 2 in their extra strings. So the things that they did is they had the download request, and the only thing that it did is it downloaded the any file that they wanted, and that file was downloaded in the Google Play app process using that inject. So whenever it was finished, they will get the download result. Again, this download was encrypted, and when I say encrypted, you all know how it was encrypted, so I don't have to repeat it. So then the other thing they did, they also did an install request. So of course, they downloaded something, they wanted to install it on your device through a code injection in the Google Play Store app. And interestingly, they used real unpopular Google Play package names the apps that they downloaded had nothing to do with the apps that were on Google Play Store. And in fact, they didn't even pretend to have anything to do with the Google Play Store apps, but they used their package names for some reason. They used those package names to install in their APKs that were installed on the device. And again, installation results simply returned that the installation happened. Then there was activation. Activation is a process, if you're not familiar with how Android apps work, after you install an app, you have to click on an icon to make the app to actually run on the device. Otherwise, it won't run and it won't be active, as they call it. So activation was a way to make the app run on the device for the first time. So instead of making the user click on an icon, they kind of wanted to automate that part. Then there was pull request and pull the results. And I'm using Google Translate here, so it's a translation of the Chinese strings that you can see on the left here to the English strings that you can see on the right here. It was all described in Chinese, obviously. That's why I'm using Chinese strings. And pull was simply a heartbeat, a kind of communication that let the process know whether the code injection was successful or not. So the process could send the pull request, and if it got the results, it meant that the inject was successful and was running. And finally, there's an uninstall request and uninstall result. Again, they need to uninstall all the apps in order to do this space management thing. And this space management thing, as I say, is done in order to save the space on those low-end devices. Okay, next thing. There is another problem that they had to solve. So now they have the get running tasks that they wanted. They can download and install app through Google Play process, not through Google Play, but through Google Play process. And the other thing they have to have is a way of communicating with the system level backdoor. It's not another app, so you cannot communicate with it using intents or any other standard Android communication mechanism. So what they did is, if the app that they downloaded and installed wanted to communicate something to the system level backdoor, it simply sent a log line, a pre-programmed, hard-coded log line that said, hey, I'm running, whatever, do something for me. So if that log line was captured by the backdoor, then the backdoor could easily know that the app is running fine. But they needed a way to communicate back from the backdoor to the app, right? And that's not an easy feat when you're running only in the log function. So what they did is they used something called Java properties. And on Android, you may be familiar with system properties. System properties are those system-wide properties that are the same for every process. Like a good example of a system property is build fingerprint. Build fingerprint is the same for whole device. Java properties are slightly different. They are specific to one process that's running on the device. So if you have a Java property, you can have the same Java property in different processes, and each of those processes can have a different value. So what they did is, because they were able to run in every single context, they were able to run in the apps context, and they were able to set up some Java properties. And the process had to know which properties to look for, obviously, but it was kind of in the know either way, because it wanted to communicate with the backdoor, right? So they were able to expose things like interesting directory paths and version number and whether the backdoor was there or not, so the app could decide whether to run or not. And there was another very specific part of Triada that was in a completely different place and seemed kind of disjoint. So the other part was in a web view code. And let me just clean this up a bit for you. So what the web view code did, and it's a snippet from the load URL function in the web view. So what the load URL function did is it checked for the system property. And if that system property was set to 1, it invoked this YH load URL function, in addition to the usual code. So what happened is if you loaded anything in a web view, you would go to the, you will get redirected to this YH function. And now I was not able to find an implementation of that YH function. It was mostly code stubs or something that didn't do anything. But based on the previous historical reference to the old Triada routing Trojan, remember I mentioned that it also did kind of a code injection to the browsers. So you can draw an analogy to this kind of behavior. So what they used the code injection in the browser previously was to rewrite add URLs. So instead of seeing ads for coming from whatever ad SDK the website used, they will redirect you to a different ad and effectively rewrite the URL for a different ad. So the user wasn't even aware that a different ad was being displayed. And that was like their whole monetization model, that they used kind of different ad networks. Okay, so we were successfully able to trace them through numerous Triada versions. The newest one that I know of is called 1.5.1, and I'm using 1.5.1 because they had version numbers, so this was fairly easy to track. And they had, and this is the changelog that I compiled. It was not included in Triada, unfortunately. So I kind of looked at two different versions and had to diff between them. And what this changelog shows is, for me, it shows that there is a real development going on. They not only care about the features that do all the badness and rewrite URLs and all that stuff, but they also do a normal, regular software development. So they change MD5 hashes that I mentioned before to SHA-1. It doesn't make anything more difficult because they only inject popular processes, so you can still like have a bunch of hashes and recalculate them. They introduced a delay. They changed the code injection framework. The newer one actually didn't was more friendly to DEX files. And then they also did some compatibility upgrades for Android Nougat, and I think they were preparing a code to add additional code to the System UI app, but I haven't seen where this went through, so there were only stubs and like random places that didn't do anything. Okay, so reverse engineering is done. The technical part is over. And we had a unique opportunity of actually reaching out to the OEMs and figuring out what to do with this. So after I bored you with technical details, here is the more human part, let's say. So how did the backdoor actually got on the device? It's not easy to get something on the device, especially if it's such a low-level backdoor. What the OEMs do, and again, I'm talking about the low-end OEMs, what they do is they want to include a bunch of software features baked into Android that are maybe not part of the Android open source project. So there are companies out there that allow them to include additional features, like face unlock or something like that. And the OEMs use those companies to include their code in their device Android system. And one of those third-party vendors included also Triada backdoor. Of course, it didn't, it didn't advertise itself as, hey, I will include this Triada backdoor. It added some additional features and this Triada backdoor, and it didn't mention anything about it to the OEMs. So what we did is we contacted 16 different OEMs that were identified with having this particular Triada problem. And this problem was on 30 different devices across 2.5 million users worldwide. And we contacted them and asked them to provide a system update that removed Triada from their devices. And this is, I think this is my favorite screenshot like ever in my whole security career. It comes from the device that's on my desk, and it was a device with Triada, and this is the system update that removed Triada from that device. And I verified that it really does remove Triada from the device. So they started providing system updates to all their users, and users are free to download it, install it, and they will get rid of Triada, which is really good. So to recap, and I don't know how much time I have left. Oh, 5 minutes, great. So to recap, Triada authors moved from a routing Trojan to a pre-installed backdoor, as I told you about. And I only mentioned this encryption routine, but of course there are different IOCs that we are basing the attribution on. And they retained more or less the same functionality and purpose. They wanted to provide a different ad experience, let's say, to the users. Reverse engineering showed multiple different code changes, which were really in line with like software development and not necessarily developing the malicious features and only concentrating on those. And we worked with all the affected OEMs that we were able to find and asked them to provide a system image update that removes Triada, and they did so. So we effectively hope that Triada won't come back in the future. And that is all. Thank you.